All right, welcome everyone to the second video here, and talking about exact and inject differentials, and now applying this to our change in internal energy. Okay, so what we know, U here is the state function, right? And let's look at this and apply now, and look at the total differential of U, considering U is a function of V and T and N. Okay, for now, we're going to assume N is constant. And the relationship of the change in U with respect to N is going to be related with our chemical potential and things like that. And we're going to talk about that later on. We talk about Gibbs free energy and eventually get into phase transitions and other things of that nature. So for now, we'll just assume N is constant and not worry about the dependence on N. And so we're just looking at U, internal energy U, right, as a function of volume and temperature. Okay. And so we have del U del T at constant volume, dt, plus del U del V at constant temperature, dV, right? That is the total differential of U. Okay. Well, right. And so when we look at this, right, if again we're assuming dN is 0, right, constant N here, right? So if we look, right, some change in volume will cause, right, some proportional change in internal energy. When temperature constant, right, we have change in temperature, right, gives some change in U when V is constant, right, and how this change in temperature affects the change in U, and this change in volume affects the change in U, is based off of these proportionality constants here, right, these partial derivatives of the U with respect to temperature. Okay. If we recall, okay, right, we've talked about what these are before, right? We spent a decent amount of time talking about heat capacity heat capacity at constant volume, right, which is del U del T constant volume, and then we introduced this idea and this concept of internal pressure here. Pi sub T is referred to as the internal pressure to the partial derivative of U with respect to volume, constant temperature here, right? And so this is giving us, right, the total differential of U then is CV dt plus pi sub t dV, okay? And so this is telling us how some change in U is corresponded by some change in temperature or volume, right? And how much U changes based off change in temperature or change in volume is determined by values of the heat capacity at constant volume and this internal pressure, okay? Right? We talked a lot about the heat capacity, right? But again, internal pressure, okay, for a gas is sort of a measure of the strength of the attractive forces, okay, right? and it's determining, right, how much the internal energy is changing with a change in volume at constant temperature, right? And that change in volume, so if you think about, right, the attractive potential between two gas particles, right? It looks like this, right? So I'm plotting like energy here, right, versus separation distance r, okay? Well, if I have my stuff compressed at a very, very, very small volume, okay, right? Let's say I'm somewhere here, right? Let's say at my volume, my average distance between my molecules is here, okay, right? Now, if I increase the volume, okay, that increase in volume means that my average separation distance increases to the right, right, which means my internal energy here, I don't need to plot this as E, right, let's plot this as U, right, my internal energy U increases, right? If I go to the right of this, my internal energy increases by some amount. Now, if I compress my gas and reduce its volume, its average separation distance between the particles moves to the left, in which case the internal energy is going to drop, okay? And that is when we're in a case where attractive forces are dominating for this molecule, okay? Now, it's sort of the opposite if repulsive forces are dominating, okay? And that is based off of essentially what the sign of U is going to be, okay? Or sorry, the sign of pi t, the sign of this internal energy, okay? Right? So if U increases with a increase in volume, that means pi sub t has to be greater than 0, right? That is related when attractive forces are dominating, okay? That's right. But if u decreases with an expansion, okay, that means repulsive forces are dominating, right? Because think of internal energy increase, okay, right? If I increase my volume, my internal energy increases, right? Right. That means I'm having to overcome these attractive forces for this volume change to occur, okay? But if my internal energy decreases with an increase in volume, that means, right, that essentially I'm giving up some energy, right? There's like an exothermic process, right? Because my molecules are able to relax, right? They're like compressed tight together, repulsive forces dominate, you increase the volume, and the molecules just, they just relax down, right? So its internal energy decreases, right? It's an exothermic process, right? And in that case, pi sub t is less than 0, okay? So for pi sub t greater than 0, internal energy increases with an increase in volume, and pi sub t less than 0, internal energy decreases with an increased volume, right? And those are related with attractive versus repulsive forces, respectively. And then finally, right, for an ideal gas, as we talked about before, pi sub t equals 0, okay? Right? Molecules do not interact, so there is no change in internal energy with a change in volume, okay? And that does it for this video talking about the exact differential of internal energy.